The attack is in your context window. This is where you'll learn to scan documents to flag unsafe chunks. Then answer a question from the safe ones so you get trustworthy results. You will learn how to spot risky document fragments quickly. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. RAG systems work by pulling text from many documents and stuffing that text into the model prompt. That ability is powerful and useful. It also opens a new attack surface. A single malicious paragraph can try to override your instructions or leak secrets. Success looks like answers that match the truth in your trusted sources, while ignoring any noisy or adversarial fragments. For a data scientist, that means higher trust in model outputs and fewer surprise hallucinations tied to bad context. At a high level, RAG-doc poisoning is the pattern where document content itself tries to manipulate the model. The simple idea is to treat retrieved document chunks as inputs that can be scored for risk. Then quarantine the risky ones before you build the final prompt. Strengths are that this is cheap and model agnostic. Weaknesses are that heuristics can miss clever attacks or overblock useful text. So you always balance safety and recall. We will build a small, practical pipeline. It will split short documents into chunks, flag suspicious chunks with simple patterns, score them with heuristics, and then show how quarantining changes retrieval. The goal is a clear mental model you can implement in a notebook and then tighten for production. Now we will split documents and run a first-pass pattern filter. This snippet splits small documents into chunks and flags likely prompt injection patterns with Python's RE module. The variable docs holds 3 short texts that mimic RAG content. The pattern R combines cues like ignore, reveal prompt, exfiltrate, and system prompt, which are common injection tells. The list CS is built by splitting sentences on periods and trimming whitespace. The final print counts how many chunks match the pattern. A first-pass filter you can run before indexing. Tightening or loosening the regex changes recall versus precision of detections. The printed suspicious count quantifies how many risky chunks would be quarantined immediately. Next, we'll assign numeric risk scores to each chunk. This example assigns a numeric risk score to each chunk using simple heuristics powered by re.search. The function risk adds 1 point for directive verbs like ignore or bypass that try to steer the model. It adds another point if the text references the system prompt, secrets, or keys, and half a point for code-like markers such as backticks or base64. A small fraction is added for excessive capitalization to penalize shouty commands. The code then picks the riskiest chunk via max over CS. Higher scores mean stronger signs of prompt injection. The printed top risk shows the worst offender's score. Now we'll simulate retrieval and show quarantine changing results. This snippet simulates retrieval and shows how quarantine changes the top result. The string Q represents a user query, and the lambda score counts shared words between Q and a chunk for a quick relevance proxy. The variable A is the best match from all chunk CS without any safety filter. The list safe removes chunks with risk at or above 1.5, and B is the best match from this safer pool. If changed is true, your retrieval result shifts once risky chunks are quarantined, preventing injection from entering the prompt. The printed changed confirms whether safety filtering altered the hit. Next, we'll compare 2 quarantine thresholds to feel the trade-offs. This snippet contrasts 2 quarantine thresholds to show their practical effect. The variable tau low is a stricter setting that quarantines more chunks. while tau high is looser and lets borderline chunks through. The lists Q low and Q high collect chunks whose risk meets or exceeds each threshold. The difference delta counts how many additional chunks are blocked when you tighten the policy. Increasing tau reduces quarantine and improves recall, but can leak more risky content. Decreasing tau catches more attacks, but may hide useful context. The printed quarantine delta quantifies how much your safety gate shifts between these settings. Finally, we'll sanitize top K candidates and measure risk reduction. This example closes the loop by ranking, filtering, and measuring safety impact. The list can sorts chunks by the toy relevance score to mimic a retriever output. The list safe cans then keeps the top K items that pass the risk threshold tau, forming a sanitized context. The variables AVG before and AVG after compute average risk for the top K before and after filtering. Lower AVG after means the answer context is safer for your generator. Raising tau admits more content but reduces risk reduction. Increasing K broadens context but might reintroduce borderline chunks. The printed risk reduction shows how much risk you removed. Mapping this toy pipeline into a real project is straightforward. Replace the toy retriever with your vector index and use a real relevance score. Run the risk heuristics as a pre-filter before you assemble the final prompt. Log which chunks were quarantined so you can audit decisions. In a staged rollout, start with conservative blocking, but only quarantine. Do not delete content. Recap what it is: a pipeline to flag and quarantine risky document chunks before prompting. When to use it: whenever you retrieve external text into a model prompt. One caveat: heuristics can both miss clever injections and overblock helpful context. Next step: tune the quarantine threshold and the top K context size to balance safety and answer quality. Try changing tau and K while measuring retrieval shifts and risk reduction. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.